All right, the different types of formulas for the definition of derivative. So I've already gone over what the derivative is, right? Again, it's just the slope of a tangent line to a curve or to a function at some point. We got three ways to solve it: numerical, graphical, analytical. We're going to do analytical mainly. So let's go on this next page here. This is the formal definition right here. We've talked about this one, but there's other ways that you might see it, and I said that this is probably the way that I will most often do it. But I wanted to show you all of these ways, these different versions of the derivative. They're all the same thing. They're going to get us the same value. And I will say this. This could also be as c approaches x, because all we're really saying is these two things become equal. So you could do as x to c or c to x. And for today, I'm actually going to do c to x so that you'll see how it turns out. It turns out more uniform to the other ones. Okay, so let's just dive into it. Basically, I got three problems. They're all the same problem. They're all the same function, but I want to use different notation. So I'm going to use the first one where h approaches 0 here to evaluate it. And we've done this one before, so it should be pretty straightforward. All we're going to do is we're going to say, let's first off say that this is f of x. That's an f of x whether you like it or not. Okay, so that means that f prime of x, that little hash up there, just prime, is going to be the limit as h approaches 0 of, and instead of just x squared now, I'm going to have x plus h squared minus just x squared all over h. Okay, we've messed with this before. We're going to expand this. And so that's x squared plus 2xh plus h squared minus x squared all over h. And this is where you can see that the x squared minus x squared just results in 0. And then we have the limit as h approaches 0. What's left here? Well, I definitely have an h in both terms here, so I'm going to factor out an h. So I'm going to write the h, and if I factored out an h, I'd have a 2x plus h all over h. And now we see how we can get rid of that h. And so we're really just asking for the limit as h approaches 0 of 2x plus h. Well, that's just 2x. So the derivative of this function is 2x. All right. Now, we're going to do the same thing over and over again. I just want to show you that we will get the same result. So let's look at the second one here. Okay, remember I said on this one, though, you could do as x approaches c or c approaches x. I'm going to do as c approaches x because I want to end with x's, not end with c's, just so we can have some uniformity in our answer. So let's just fill this thing out. F prime of x equals the limit as c approaches x of, well, what is f of x? Well, it's just x squared minus c squared over x minus c. Okay, well, what is this? Well, this is really just a difference of squares, isn't it? So I could say that this is the same thing as the limit as c approaches x of x plus c times x minus c all over x minus c. Hey, look at that. Again, we get some factors that are going to cancel out here, and so this is equivalent to the limit as c approaches x of just x plus c. And now there's no reason why I can't just plug in an x for c, right? So that means that this thing just equals x plus x, or, hey, look at that again, 2x. And so we've seen that it doesn't matter which of these two formulas you use, we get the same thing. I had to erase it because it was being funky, but we did find up here that this also equaled 2x. And so my point is just that you see it doesn't matter which equation you use, you'll end up with the same result. Let's go to the next one just to see it. Okay, here's another definition of the derivative. This one uses some a plus h and some a minus h. And that would mean on the bottom you get 2h, right? So if you had 2 points, one a plus h, one a minus h, the distance in between those in terms of x would just be 2h. So let's plug this in. So f prime of x equals the limit as h approaches 0 of, well, a plus h inside x squared. That would be a plus h squared minus, parentheses, a minus h squared. And I think that this negative sign is going to be relevant here, and so we're going to need to keep track of these parentheses over 2h. Okay, the limit as h approaches 0. We could expand this now. This is a squared plus 2ah plus h squared minus, let's use parentheses. This is going to be a squared minus 2ah and then plus h squared all over 2h. Okay, let's distribute this negative. We would get the limit as h approaches 0, a squared plus 2ah plus h squared minus a squared plus 2ah and then minus h squared all over again 2h. And now we can see, hey, I have an a squared minus an a squared. That's nice. Get rid of that. H squared minus an h squared. Get rid of that. And so I'm really just looking at the limit as h approaches 0 of 2ah plus 2ah. These things are exactly the same, so we're just going to make that 4ah over 2h. Hopefully you see these h's just kind of cancel each other out, and you can take a 2 out of both of these things. So really, this is asking for the limit as h approaches 0 of, all we would have left is 2a. And the important thing here is, once you don't have an h in your expression anymore, see there's no h over here, there's no need for the limit notation because there's nothing to evaluate here. So this just equals 2a. And let's go back to the very beginning. I could have done this from the very beginning, but what is our a value? Well, it's f prime of x, and so I actually kind of made a mistake here. Everywhere that there's an a, I should have had an x, but that's okay. We could just replace it at the end here. So instead of 2a, this equals, well, 2x. And so we once again find that the derivative of x squared is 2x. Okay, so all that work to find this. Again, I kind of made a typo here. It's not really a big deal, but we were evaluating the derivative at a, and I was actually trying to find the derivative at x, but that's really simple. I just replaced the a with the x, and it's the same thing. So, maybe what I should say here is that this is the derivative at a, and then everything's fine. And if the derivative of a is 2a, the derivative of x is 2x. There we go. So we found the same equation on every single one, and so I just kind of wanted to show that to you. It doesn't matter which one you use. Again, the first one is the one I like the most, but it doesn't matter which one you use. You're going to get the same derivative every time. All right, see you guys on the next video.